Now let us look into the symbol tables that are created by the compiler for the respective input files. And this symbol table is a part of the object file, as we discussed, and we briefly had a glance at the symbol table. We didn't talk about it. So just like the relocation section is one area which the linker needs to know of for fixing the fixing the addresses and function call addresses and variable addresses and so on, symbol table is another important important table or a collection of data that the linker needs to know about. And this is the structure of the symbol table. We'll also see it in the terminal. Now this is the structure of the symbol table, and this is the symbol table for the first input file, that is the real example main.c. Now the symbol table informs the linker about the global variables that are available. And this, okay, so the symbol table has information about the different sections, that is the text data. So these sections are also treated as symbols. And then arrow data, all of these are treated as symbols. Global variables are treated as symbols, functions are treated as symbols, and static variables within a function will be treated as a symbol. So we have not seen an example of a static variable as such. Let us see an example also of a static variable. So we'll do that after this. So anyway, so we can see the symbols here. That is, whatever symbols the compiler is aware of. It talks about the size of the particular data. If it's a data structure or whatever it is, it gives the particular size of that structure. For arrow data, again, for the variables test1 and test2, because it is read-only data. Test1 is I think it's a char, and this one is again an unsigned int. So the size of those symbols are given. They don't have any size as such. They only have addresses. But again, since this is the initial output from the compiler, all these addresses are not fixed. They are just offsets here, you will see. So these addresses are not fixed. And then we have different variables here, and the sizes of the variables are known, offsets are known, but then all of these symbols are going to be fixed by the linker once after the linking process. So you have these variables: test3, test4, test5, ep0 state machine, ep2 state machine, so on and so forth, until you come here and you see UND. So this means the compiler has no idea about these symbols, because these are function calls belonging to other files, and the compiler does not know. As we discussed, the compiler has no idea about what these symbols are. And of course, these are, these are LLL. These stand for local. These are global symbols, and this is undefined. It doesn't have any idea about what these are, and these will be put into the relocation section. This is in brief the symbol table that you have for the first file. So let us go to the second file and check up the symbol table there and see what we have. And there is also even the file name is considered as an entry in the symbol table. So that is what we have here. So it's local and global. And then if you want to actually know what these column stands for, there is a link that I will be putting in for you, where you can actually go through all the groups of variables that the symbol tables have, which define certain characteristics or properties of these particular entries. Okay. So going to the next one, this is the symbol table for core initialization .c. So again, you have the text data VSS section, and there you have only one symbol that is undefined. Rest of the symbols are defined, but of course the addresses are not fixed again here. The third one for startup GCC, again, you have quite a few undefined symbols. For example, the sysdig handler, The reset ISR is it knows where the reset ISR is within that particular file. What static handler is undefined, BSS, EBSS main. So these are symbols that are there in the linker script file actually. These are the symbols that are there in the linker script file. So this is not even, these symbols are not even there in any of the C files. When the linker actually completes the linking process, it will populate these symbol values, okay, in the table, and the calls to these symbols, or rather the references to these symbols, will also be fixed. So having said that, we will also have a look at the reference to these symbols after having a look at the symbol table. So this is in the startup gcc.c. You can actually run the obj dump command, and if you look at the startup gcc.o file, you'll see where in the reset ISR these symbols are called. In the beginning, they will not have any branch addresses. The branch addresses will only be seen in the output file. So this is the final symbol table, that is the output from the linker. And as you can see, first thing that you get to see here is there is no undefined here, no UND. So it's like .text BSS. It clearly has inserted all these symbols into their respective areas, and there is nothing unknown here. Everything is known. Okay. So again, the D stands for data, DF stands for function, okay, and so on and so forth. Okay. And we see that all the symbols have been fixed, including those symbols where you have the, just a moment, .bss, EBSS, CTXT data. So let's see where those are there first. See, so .bss, .ebss, all of them have been fixed. So see, they have been moved around. Now the symbols were all in zeros, right? So it starts from 800. So anything in text goes into 800. Anything in data goes into 20000000, and so on. So the BSS section starts from 20004, and debug info starts from somewhere else. All the addresses have been fixed. Data goes into different in the RAM. So this is the address, and this is somewhere in the RAM. Text data goes somewhere else. Okay. So all the symbols have gotten fixed by the linker. There is no unknowns here. Now let's have a look at the map file, and we'll see what the map file depicts and what is the content of the map file. So the map file has already gotten created here. So we'll have a look at the .map file here. So this is the map file, and this is a text file, so you can straight away open it. It's not an object file. So this talks about the memory configuration of the output file that the linker has given out. So you have it tells you about the memory layout which we have given it in the linker script file. So we'll see it shortly. So the flash starts from this location, and the length of the flash is this. Okay. The SRAM starts from this location, and the length of the SRAM is this. Okay. There is a default memory section, and then the actual memory layout starts. So it says that the text section starts from this location, that's the flash location. So for STM32F4XX processors, the flash starts from a different area in the memory. For other controllers, it will start from, probably it will start from 0 or some other memory location. So we have the dot. So dot equal to the underscore text section is just a way of saying that the text section has this counter now, this address now. So this is what the text section now has. Okay, and then this is the end of the text section, and then one part of the text section ends here, and then you have the ISR vector section, which is in the startup gcc.o, and the size of that particular section is 0x194. The size of this text section is 0x54c, and this has your the vectors actually. Okay, and then again another text section which is your main. So the main section that we have, the build example main.o file. So you have these two functions here actually. Okay. So these two functions, and this is the size of that section. 0x5c is the size of the section, and it says that this function and this function are starting from these memory locations. So this map file is quite elaborate. It gives you a lot of information about what is present here. So this is again the core initialization file that we saw, and then the size of this file is 2e4, and here are the functions and the locations of the functions. Okay, and then again for the startup gcc.o file, you have, this is the reset ISR in the text section. So this ISR vector has gone in here because we, in the linker script file, we had asked the ISR vector to be put in here, and for the startup gcc.o file, it has come here because this is a text section that we have asked. The linker has put the text section here, and it's no harm because this is fine. And then you have the build example main.o. So build example main, again you have this is the read only data section. Okay, so this text section ends here, and then you have the read only data section. So read only data section, because these are constant variables, you have two values. So this section is 8 bytes long. Okay, now this section is startup gcc reset ISR is 0x70 bytes long. So I'm saying 0x70, but if you want to know what is 0x70, you just need to do 70 here, and you'll get the decimal value. So it is 112 bytes long here. See, check this out. Okay, anyway, moving on. So you have the RO data section. So RO data section, again we saw it has test 1, test 2. Then you have the glue sections, and you have some glue sections which is not important to us. And then we have the data sections. Okay, so data section, there is one data section which has a load address. So and then we have the data stops here, and then we have in the build example main.o again. So we have some data. These are initialized data that you have. Okay, EP2 polling rate test 0. So these data actually has to be moved to the RAM. Okay, and then you have core initialization STM32. There's no data here. As you can see, there is no data on initialized data here. You have initialized data here, that is in build example main.o, and then you have this one. You have the startup gcc.o, which again does not have any information. There's no data that has to be moved into the RAM, and the e data, that is whatever you see, we'll see that in the linker file. The e data ends at this address location, that is 2000005. Okay, this is the layout. Now coming to the BSS section. So BSS section again has load address of the BSS section is this, and then BSS section starts again for build example main.o. There are a lot of uninitialized variables that has gone into the BSS section, as you can see, and the size of the BSS section is 0x279c. So again, this BSS section has data buffer in EP2, test 3, test 4, test 5, and so on and so forth. Okay, and then again, this is another BSS section which holds a random variable under core initialization STM32F411XC.A. Okay, and this ends your BSS section. Now these values are important because we will be using them to calculate the size of data that we need to zero initialize in the BSS section. So we'll see that. We'll see that when we are looking at the initialization script. Okay. So now let's go back to this and let's see. So yeah, we have found our variables, like we have found where EVSS is, eText is. So let's see here, eText, so let's see where eData is now. So eData, let's check up where eData is. So all of that has to be resolved here. Okay, text end. Let's say where the e-data is. Here you see the e-data has come here with an address location. So all of that, all the symbols have been resolved, because in the output file and now when the binary goes into the board and it sits on the board in the flash, none of the symbol informations will be there in that binary file. So of course, in a startup file, when all these variables are variables from the linker file are accessed, the linker actually has to fix those variables in the startup. So let us do one thing. Let us check for that. We already have the output here, so let us check for the startup reset function that we have in the linker, the reset ISR, whatever you have. Now let us see if we have, if this value has been, so this is a value that is in the linker script file. Okay, so let's see if we have this value resolved. So as you can see, this value is PC plus PC plus 64. This is 80051C. So let's go to 80051C and see if that value is, and you can see previously this value was not there. Now this value, that is the E, this is the value for, let's say this is the value for eText. So eText, the eText value has been fixed to 80051C, that is this one, 80054C. Okay, this is the value of. Similarly, all the other values have been resolved. So let us go and check in the symbol table if eText has this value. If eText has this value, we will know that, and the value will be in the, the value is the address here. So we'll talk about that. The value will be 0, but this is actually the address of eText. So let's check this. So where is eText? Say here is eText, and 8000558 is the eText value. So let's look at this. So it says 8000554C. So maybe whatever we are seeing here is older value. Let us do one thing. Let us go in and check the symbol table here. Okay. So whatever we are seeing in the in the slides, maybe a different. When I took a screenshot of the slides, maybe the code may have been slightly different. But let's go in and check the symbol table and see if eText is whatever we want it to be. So let's go for eText. So it is 8000554C. Let's come down. Let's see what eText value is. So let's go to so reset ISR, and then you have eText. eText is in 80051C, and when we go to 80051C, we see the value is 80054C. So what we have in the symbol table is right, but this was probably, I had taken the snapshot with a little bit of difference in code. But then if you want to see the real-time values, you can actually come here. So this is, as you can see, this value is the right value. So 8000554C. Here we have 8000558. So maybe here there were certain few things that were different when I had taken the screenshot. I hope you get the idea as to what is really going on. Coming back to the build example.map file again, which we discussed earlier, you can see a section called common here. So there seems to be some ambiguity between the GCC version, older GCC versions and the newer GCC versions. In the previously, for uninitialized variables, for example, if a global variable was uninitialized, it seemed to go into the common section. So if you had certain variables which were uninitialized, say outside main, you just declare an int x, this would go and sit in the common section previously. But right now it seems with newer compiler versions, ARM GCC compiler versions, both initialized and uninitialized global variables, that is global variables which are initialized to 0 and uninitialized global variables, all go and sit in the .bss section. So you might come across, sometimes you might come across certain map files where you will see some elements in the common section, but if you use the compiler version that I'm using right now, you will not see this happening, and the common section is going to be empty. So let us do one thing. Let us check the version of the compiler that we are using right now, and let's verify that. So ARM let's check for the version. So we are using the GCC version 10.3.1, which is 2021-0804. So this version is quite recent. So this common section comes in only because it has been put in the linker script. So the linker has an instruction to include the common section because we might be having certain things coming into the common section, but we don't see anything. However, it is advisable that you keep the common section here because we do not know. I mean, I'm still not sure about the behavior of the compiler, or when I have not seen it. I have tried with the latest with the recent compilers. I've tried a lot of combinations, permutations and combinations, but no variable seems to be coming into the common section anyway. But still, it is advisable to keep it because I may have missed out on some scenarios. There are a few other things that need to be discussed about the map file that I did not discuss, or I deliberately left out in the last discussion when I showed you the map file. One is, if you see here in the .bss section, there is a location which occupies about 400 hex of data in startup.gcc.o, okay, and it says it's a pull stack. Now this is the variable which holds the stack information. So that's why you see it here. Now between the previous discussion and the current discussion, I made a slight change in code, which is why you are seeing the variable name here. Previously, if you see the previous video where I had dealt with the map file, I would probably passing this place and you would just see this value here and not the variable underneath. And I will explain you why that happens. Okay, so that's again something pretty interesting, as to sometimes you will see the space has been taken up by the particular object file, but you don't see the variables. For example, you see the variables here, space has been occupied, and you also see the variables here, but in some cases you don't. Okay. There are also a few other things that need to be discussed. That is, there is something called as fill here, and this also you did not see in the last demonstration, because I have added a little bit of I've added a little bit of code to demonstrate this for you. So now what happens here is, inside a section, within a section, if something, for example, you have core initialization, within this you have two variables, and if these variables don't end in a word alignment, then automatically within that section the linker itself will be adding paddings, which is called fill here. So see, it ends in 410, which is not aligned. So it adds 0x2 so that the next one is 414. Okay. So that is something that the linker will do within a section to keep this aligned. Similarly, in the BSS section, if you see, there will be some. Let me drop this out. This is. So let's look into the BSS section now. So this is something that we were seeing in the BSS section. Now, if you see in the data section again, there is a value here. So in the core initialization, so here you see that the core initialization has taken up some space, but you are not seeing which variable is taking up that space actually. So we will discuss about that. But here also you see that within the data section, there is an alignment issue which is filled up by this, and again an alignment is made by the linker. So it starts from here. Okay. So again, this section takes 6 bytes and it ends here. So 6 means 6 plus 4 is 10. So this is the end of the 6, 7, 8, 9, 10. So this is the end of that particular section, and then the BSS section starts. If the section ends in an unaligned byte, the linker does not bother, but within that section it does a check to see if the alignment is proper or not. So there will be, when you verify, sometimes you may not see the fill at all. There is another interesting aspect of linking, and that is the order in which you put the object files, or order in which you present the object files to the linker. For example, in this case, we have the startup gcc.o first, core initialization next, and the last is build example.main. So when you look at the layout here, that is how the linker has laid out the memory, you'll see that startup gcc.o comes first in every section. In the text section, the same happens. If you go to the data section again, the data is also organized in this way, except for the fact that we are deliberately having the ISR, that is the ISR vectors. Wherever you declare startup gcc.o in the linker, we have forced the ISR vector to go into the first, that is the first location of the flash, which happens to be this in the case of 8 with 6 zeros. So this is what is the location for STM32. So this will anyway be there, okay, because we have done it that way, but the order of the files after that does not matter. For example, what we'll do now is we'll interchange, or we'll just move around the order. For example, we have startup gcc.c.o and core initialization. What we'll do is we'll bring build example.o in the middle here, and you can try various permutations and combinations, and let us redo the compilation and see how the map file looks like. So you will see that the map file has changed. So let's see. So let's clear this and do a. Okay, we have some error. So we are facing some errors in linking. So startup. So we have build example.out, startup gcc.o, build example main.o. Okay, so we committed a mistake here. I forgot to delete this part. That is the last one. I moved around and put the build example main.o here, but I forgot to erase this. It should work now. So let's have a look at the map file. So reload the map file, and you'll see that here this is the same. This part will be the same because we are forcing it. Otherwise, you see that first startup gcc.o information has come in, then build example main comes in, and then core initialization comes in. And depending on that, if you see the because we have arranged the files that way, I have not given it a thought. I just randomly arranged the 3 files, and you'll see that the fill, whatever fill we saw, are missing here. That is because now we have arranged the files in such a way that it has got word aligned. Okay, so word aligned in such a way that the fill is no more necessary if you arrange it in this way. Not always will this happen, but all I'm trying to state here is, when you probably try it out, and if you give a different order of files, you might not see the fill here, and this is the reason. Now let us go back and arrange the files in such a way that we again get the fill. So what did we do to have the fill there? So we remove the build example main here and keep it in the end. So that was the arrangement in which we saw the fill coming in. So let's keep that arrangement here. Let's keep the organization of the order of the output files in this way, so that we can see the fill. So let's do it once again. Let's see if we get the fill now. See, the fill has come back because we changed the order of the files. In the data section, we see that core initialization STM32F411. This file is occupying 2 bytes of space, but we do not know how. Okay, we are not sure. This one would have anyway been occupied. I just rearranged the file so that I could show you that different file arrangements would actually result in different layout in the map file. So don't expect your map file and somebody else's map file to look exactly the same. It all depends on how you organize the .o files and to be put into the linker. Okay. Now coming to why we are seeing a space that being reserved, yet we are not seeing the variable. Now if you come here to core initialization, that variable is actually this. Any static variable that you declare, so any static variable that you declare within a function or outside as a global. So I don't know, I don't declare static variables in global spaces, but it generally makes sense to declare static variable within functions, and that's the practice I follow. Any static variables that you declare will have space. It will definitely occupy a space. And so if you declare a static variable within a function, it is like a global variable, but the scope is within the function. Now if you if you do an obj dump of this file, the core initialization stm32.o file, you will see that this value is recorded. That is, in the symbol table you will see this value, but this value will not be shown in the map file if you declare it as static. So let's have a look at the symbol table. It will become more clear. So let's do arm none bi obj dump. Okay. Now let's look at the symbol table. If you see the symbol table, you see this value. It's an object, and this is object, and this value is recorded here, but test7 will not be visible in the map file. Okay, so this is one thing that you need to be aware of. Also, there is one more static that I have declared within the main. Let's try to find that out. So if it's a static within the main, then it's going to go in the static is always initialized. So let's see where it goes. So build example main.o, and this is occupying say 6 bytes of data. Now you might not understand it straight away because main also has some initialized variables here. Okay, so how did I find this out? So we'll do one thing, go back to the code and we'll go to the main. We'll go to the main. Okay, see, this is a static declaration that I have done here. Okay, let's comment it out and let's run the whole thing again. So when you comment this out and you run, don't get confused. Repeat the videos, watch it over and over again, and these concepts will become clear to you. Maybe when you begin, it might look a little bit overwhelming, but as and when you go through the videos, it should become simple. So now let's go to that part where we had seen the main, and as you can see here, the usage has come down to 5. See this? Now it is not showing the variable that you're using, and definitely the other part is again the same. That is build example main.o, whatever we had is, sorry, the core initialization is still using this 2 bytes. Now it is using 2 bytes because I have declared that variable as uint16. Okay, it's short, so that is why it's an unsigned short, you can say. So that is why you are seeing only 2 bytes occupied here. Sometimes the total size may not make sense to you because probably it is doing some padding internally. So this is the overall logic. Now we saw that, now we see that it is 5 bytes. So again, let's uncomment that section. So let's uncomment it in the main, and we'll go back to the map file. So Control S, and then let's run it. Now you'll see that I'm running it from both ends. I'm running it from within the IDE sometimes when I have to debug, and I'm running it from outside also. Sometimes it causes some issues, in the sense the cube ID sometimes gets confused if you are doing a compile from outside cube ID and doing it from within cube ID at the same time, one after the other. I have seen that happen. So when you try these exercises out, I would recommend that you make a copy of this folder which contains the code, say chapter, say this is the one. So when you download this code, I would recommend that you have it in a separate location. Just copy it, make a separate copy, and don't use the one that you are using in the IDE. Keep the IDE separate. Otherwise, there might be issues. Okay, the IDE might sometimes get confused because you are actually working on those files separately. It doesn't. If you do a project clean and redo it, most of the time it works. But to be on the safe side, it's better to stay away from the practice of working on the same code base through the IDE and from the terminal. If the IDE is closed and you're just working on the terminal with the same code base, I think it's fine. Just a heads up, just a word of caution. I may be wrong. This is something that I found, but then again, sometimes these IDEs can become a little bit unstable, this Eclipse-based IDEs. So now we have uncommented this, and let's run the compile again. And let's look at the map file. So when we look at the map file again, as you can see, the size has increased by 1 byte. You don't see it here, but the size has increased by 1 byte. Okay, one more thing. Okay, this is something that I should have shown you. Now, since let's comment this out once again. Okay, let's comment it out and let's run the whole thing. So the size has increased, as you saw. So static size increases, you don't see it in the map file. Now let's compile it, and let's look at the symbol table once. Now that we'll look at the symbol table for the main now, because objdump will anyway show the symbol. So I'm sorry what this is interferes with the screen. So build example main.hook. Let's check up if in the symbol table we can see this one. The symbol is test static. So let's see if we can see it. So we don't see that symbol here because I commented it out. You have to indirectly deduce that the variable is active, seeing the size of this, that is pre and post. Or you can check the symbol table anyway. So that will give you an idea that that variable is definitely considered. I briefly told you what the values stand for. For example, this column. We'll do a recap of that, and we'll go through a document which talks about these values, what these values stand for, and we'll also briefly go through the manuals for objdump and redelf now. Okay. So let's first check this. So L stands for local, G stands for global. This is the symbol table for objdump. Okay. Symbol table that you get out of redelf is something that we already discussed, and you have the keys below, so you can actually look at the keys, and from one column you can actually check what values are there and what the values stand for. In the case of objdump, let us go through a document and check. So let's do this. This is something that you will find online as well. So this column 1 is a symbol value. Okay, and column 2 is a set of characters and spaces indicating flag bits that are set on the symbol. There are 7 groups. Okay, so group 1 is L. So if you see in here, if you see L, G, or an exclamation mark, it means it's a local symbol, it's a global symbol. Exclamation is neither local nor global, and nothing means it's neither local nor global, and exclamation means it's both local and global. Okay, so that's group 1. That group 1 means this is one combination. Another one is W. So it's W means it's a weak symbol. Group 3 says it's a C. C means it's a constructor or an ordinary symbol. So this is something that you will probably not see in C language. Okay, so probably this is for C++. Group 4 is W, that is a warning or a normal symbol. Group 5 is I, which is in direct reference to another symbol or normal symbol. I have not seen this much. Group 6 is small d, capital D, and nothing. So it's a debugging symbol, it's a dynamic symbol, or it's a normal symbol. Group 7 is capital F, small f, and capital O, and nothing. So symbol means capital F is a function, or small f it's a file, O it's an object, or nothing it's a normal symbol. Column 3 is where the symbol lives. ABS means not associated with a certain section. So you will see the function names. So we'll go back and have a look at the symbol table. Column 4 is the symbol size or alignment, and column 5 is the symbol's name. So let's have a look at the symbol table again. So we have DF here. Okay. So what does DF stand for? So DF means it's a debugging symbol, and F means it's a file. So let's see. So of course it is DF, and it's absolute. So absolute again means, if you come here, ABS, when it says ABS, it means that this is even though it is there, it is not linked to So the section in which the symbol lives, ABS means it's not associated with any section. Okay. If you again check up the symbols, these are all debug. O are objects. This is a function. Of course, it's a function. These are also functions, but as we discussed, the compiler still doesn't know what it is. This is again a function, demo relocatable, because it's in the same file. It knows, but it's still the linker has to still fix the address over here. But that is what it is. Now let's go and check up the obj dump and readelf manuals. Okay. Let us go to check the obj dump manual, and so we will actually look at the obj dump Linux manual page, and I will talk to you about the options that we are using mostly. Okay, so these are the options. So if you go to the manual page, you will see, you can give different options to get different outputs. For example, -d is some option that we often give, and that is disassemble the contents of all sections. That is, even if it's a data section, it does a disassembly of the data section as well. So this is one. No address means you don't print the addresses on each line, but I printed the addresses to show you how the relocation happens, because the objective here is actually to show the how the linker works, right? So this is an option we have not used. This is file headers, file offsets, section headers. So it says display summary information from the section headers of the object file. So you could just try that command out here. Let's see. So we can do obj dump, but we just do a -h. Okay, -h, and it only shows you the section headers here. So we have the corresponding command in the case of readelf also. So let's do a readelf, and readelf is a generic command, and you don't need to actually do a arm readelf. Okay, readelf is generic. So if you need to print out the header, the command is different. For example, you have to give readelf -s. So if you do readelf -s, you get the same value. That is the header information. The layout is different as we discussed. So the layout is different definitely, but this is how it is. And the flags like AX, I, WA bear a slightly different meaning from what we see here. For example, AX means it's allocatable and executable and so on and so forth. But if you look here, it also gives the same information, but it's laid out in a different fashion. Going forward, you have other options in obj dump. So the options that we mostly use are, I mostly use is X and S. S means display the source code intermixed with assembly, and we talked about this where remember we discussed about not putting the debug symbol and not seeing the source information and so on. And -x gives a lot of information, and -x is equivalent to having all headers, and it is equivalent to specifying all these options together. So I generally give -x and -s to see the obj dump values. So this is in brief what are the options that you have for obj dump. So you can always come to this page and check up in the Linux manual page for obj dump and check for the options. If you have any doubts about the options, this is the page to check. Now we can check let's check the readelf, because so readelf manual. So If we go in and check for the read-elf manual, let us see what we get. So you can check it here. Read-elf again has similar options, and the options that I use mostly are -A, which is display all. I use this one, and I use one for the file header and one for the section headers. So these are the three options that I use for read-elf. So if you want to actually look into read-elf, you can come here and check. So these are a few points that I needed to discuss with you. And I think this winds up this part of the discussion. And going forward, we will actually get into the linker script and how things work. So we'll see you in the next lecture. So the job of the linker is symbol and segment relocation, as we know. And we also saw the output object file, and we saw how it fixes the addresses and function call addresses and the address locations that actually should be put for it to run on the board. But then I just have prepared some slides for a recap. So after allocating storage and gathering information about the symbol of all input objects, the linker starts the symbol and segment relocation process. So first pass it checked for all the symbol tables, all the relocation information, everything checked, and then most linkers unify segment and symbol relocation by treating each segment as a pseudo symbol. That is, segment and symbol relocation, that is, it treats the segment also as a symbol. So the segment is also treated as a pseudo symbol, and it makes it a special case of symbol relative ones. For example, we saw this before. These are actually segment names, but then it is treated as a symbol. So that is what is meant as a pseudo symbol. Okay, and data addresses are also adjusted. So this is one example. So we saw this before, and we talked about this, that before linking you have addresses as offset. Our addresses start from 0, and you have 7A, 7B, 7C, and this offsets, you have 110, 114, and this is 152, 148. After linking, you see that this address has been adjusted to 8000268. Now this is not exactly the same as what we might see now, because we may have added and subtracted some code, but this is the general idea. So now it has all been moved, and including these values have also moved to such memory locations, which actually keeps these offsets the same. So this has moved as one unit. So this is kind of, we saw this. This whole thing has just moved down. So no change here. This whole thing has just moved down to this memory location. Okay, that's all that has happened. Now, after allocating storage and gathering information about the symbols of all input objects, and after that, absolute program address reference within a segment are adjusted. So before, so first is the data addresses are adjusted, as you can see here. So data addresses were adjusted, and then absolute program addresses reference within a segment are adjusted. Now, within a segment means you have, we saw that demo relocatable function within the main, and it was the same. So we saw another one where we saw toggle LED. Now the toggle LED, even if it was the same, it was in the same file, it still needed relocation. Okay, even though, and it's the same case here in the main. It even before the compiler actually has already given it a branch and link address BL48. It has given to this, but still it needs correction, because when it moves to the final memory location, as you can see, this location, the difference here is also the same. It just moves down here. So, but then even then it is this symbol is this is in the relocation table, and then the address is changed to 8001 DC. Moving on. So what happens after that is intersegment program references are adjusted. So intersegment program references means, previously this was a program reference in the same segment, that is in the same text segment of the main file, you had two programs here. We discussed about this. The enable sysdig is in a different file which the compiler did not know of, so it did a PL0 here because it had no idea about where that function is. And if you have a look at the symbol table also for this one, so enable sysdig, it said undefined in the main function. Okay, so that is what we are seeing here. It was BL0, and then after linking, this has been fixed. It has been fixed up by the linker. So I hope you are able to understand what the linker is doing. It does a lot of work actually. And then references to global symbols are resolved. Okay. So you see this global symbol enable sysdig, which is undefined. Okay, and in the particular function, so enable sysdig wherever it is called is undefined. Okay, and so these are from actually two separate functions. It's in a different text segment, and then it is after linking, this is actually fixed. That is, enable sysdig is actually fixed. Okay, so this is what is also done, and this is a function, and this is undefined no type. So probably this call was made from, so let's go back and let's check the main. So this is the main symbol table, enable sysdig. As you can see, this is undefined. Okay, so this is but if you see in the core initialization, enable sysdig has some, it knows about its functions anyway, but then when you go to the final file, you will see enable sysdig has been finally fixed. That is, it has a proper address here. So it is in this location, and this is the size. So this is how this one was. This had no type. So, and it was a default undefined in the main. This was the function, that is the core initialization function, which had some information about the enable sysdig, and finally this is resolved here. And this is probably this extract is probably taken from readelf, and that is why it looks different in this case. That is this is taken from obj dump. Okay, and this is taken from readelf, and that is why you see some difference here, but actually this is conveying the same information.